Okay, let's see in this video about support vector meshing. All of us know how exactly SVM method works. What exactly SVM does is it separates data points into two classes using the decision boundary. We call the decision boundary to be a hyperplane. Of course, there is a figure for it. One can see from the figure. That I will just write the equation for SVM, then talk about quantum SVM. Yeah. The equation for SVM would be something like f of x is equal to signum function. In short, we will call SIGN sin W transpose x plus b. Okay, f of x is this. If we have data points xi, yi, where yi are plus or minus 1, then SVM finds f of x. Suppose if you have data points xi, yi, where yi is equal to plus or minus 1, what exactly SVM finds is f of x is equal to signum. Of course, your y is nothing but your f of x, w transpose x plus b, such that the margin between both the classes is maximized. The margin between both classes is maximized. That is minimum of w comma b, one minimum of the norm of w omega whatever, such that yi into w transpose xi plus b is greater than or equal to 1. Yeah. For nonlinear data, a kernel trick maps xi to phi of xi into the higher dimensional space. Nonlinear is when all of us know when I have the terms in powers more than 1. Okay, yeah. Now coming to this figure, just see the middle line over here. This line is nothing but theta transpose x minus b is equal to 0. The above is theta transpose x minus b is equal to 1. Of course, it can be theta, it can be w, omega, whatever. And the below one is theta transpose x minus b is equal to minus 1. Okay. Now the hyperplane divides the set of two classes. Okay. Now I can as well give you the notation for signum function. How signum function is defined. You might be knowing it. What that is SIGN of x or z whatever is equal to plus 1 if x is greater than 0, 0 if x is equal to 0, minus 1 if x is less than 0. X less than 0. The signum function simply indicates the sign, positive or negative, of its input. Okay, formally if I say it is something like this, it can be omega, of course it can be theta, guys. Now exactly what's the procedure that is involved in SVM is this. Now coming to quantum SVM, as I have made a mention, when nonlinearity comes into picture, the kernel is paired to a different, different dimension phi of x. Okay. Now, when it comes to quantum SVM, what happens is The kernels, whatever are there, are kernel. I will just write here. The kernels are defined in quantum way. Okay, let's see the quantum way of defining a kernel and then proceed further. Okay, the major difference between SVM and quantum SVM, the development that has happened in quantum SVM is all about choosing the kernel in quantum way. Okay, usually it is denoted by K, Xi, Xj, K for kernel. These kernels are usually defined as inner products. Okay, of course, usually kernel is this, but in quantum, we will talk about the functions kind. Okay, usually we define it like phi of xi, comma, phi of xj. It is nothing but we use this to define this kernel, either quantum swap test or inner product. Okay, it depends on the problem under consideration. Okay, if at all if the kernel is defined in inner product sense, then how does it look like is what I will write here. Of course, I can denote it by Kij instead of writing such a huge notation. It is nothing but in terms of inner product. All of you know how to find inner product. Only thing is in quantum writing things are a bit tedious. Okay, yeah. Quantum kernels, when defined in terms of inner product, are this. Let us see the procedure involved in quantum kernels. Of course, first the given data, whatever is there, xi would be encoded. Xi, whatever is being given to me, xi, y, whatever, what the vector that is being given to me is encoded into encoded into quantum way, quantum state, of course, quantum state, phi of xi. Okay, for example, of course, I can show how phi of xi can be. Phi of xi using you're partially aware of quantum Fourier transforms, right? X1z e power I x2 z. Of course, when applied on some initial state get 0. This is for a 2D data, for a two-dimensional data. You can define the quantum state phi of xi to be like this in terms of course, feature map. This is called feature map. Okay, yeah. Yeah, without loss of generality, let us come to the steps involved in quantum SVM. The four major are four steps. First step is encoding the data. Of course, encoding, how do I do it? Suppose if xi is the vector that's been given to me, xi be the vector given to me. Vector is a classical state, guys. Vector is a classical representation. State is a quantum representation. How do I encode it? Suppose if I am using feature maps, or feature maps are in a way nothing but your quantum Fourier transforms. Okay, and, both are not z. One can be z, the other can be x. X on the initial state get 0 is what I will. X on initial state get 0. feature maps on the initial state get 0. This is how, if I'm using feature maps, I'll encode the data like this. There are different versions, of course. I can as well go with normalizing the vector kind of things. Okay, now normalizing usually I don't do. I do it for linear regression and HHL. Of course, for the other things here, it's all about SVM is more about kernels. So I'll be making use of quantum Fourier transforms only. Okay, once this is done, next what I will do is I will compute the kernel matrix. As I was mentioning earlier, I'll compute the kernel matrix Kij. Okay, again, as I have mentioned, here I'm going with the inner product. Okay, I can as well go with the quantum swap test, guys. Quantum swap test way of defining the kernel is also there. Okay. Next is, that's it. This is the maximum thing that I can do using a quantum. I'll feed the kernel into the classical SVM only. Already in Python, you have this code for classical SVM. Okay. You feed this to the classical SVM solver. Okay. Feed the kernel into the classical SVM. That is to the classical SVM solver. What I will do is we feed quantum kernel matrix, of course, to train the classifier. Okay. Okay. Once I have done this part, next it is for me to classify the new data. That is what? Encode the new points, encode new points as quantum states, encode new points as quantum states, and input their similarity with the trained, encode new points as quantum states and input them to see the similarity, to see their similarity with the existing quantum states or with the trained support vectors. Encode new points as quantum states and input them to observe their similarity with trained support vectors, with a trained support. Of course, I can show you with a small toy problem what exactly I'm talking about. Okay, let's do one small toy problem. Of course, anyways, the feed is for the I'll be feeding it to sklearn. Okay, I'll just repeat the steps once again. What are the steps involved is encode the data. First step is encode the data. Second step is compute the kernel matrix. Of course, I'm not talking about the normal kernel. I'm talking about the quantum kernel. Calculation of the quantum kernel is what quantum kernel matrix is what I will do. Next, once I finish calculating the quantum kernel matrix, I feed the kernel into the classical SVM. Of course, to train the classifier with using this quantum kernel matrix. Okay. Once I finish training the classifier, I input uh, with more new points by encoding them into the quantum states, and hence those points similarity with the trained support vectors is what finally I will observe. Okay. Yeah, of course. A small example we can do. What that is suppose if I have, suppose we have two 1D data points, one-dimensional data points. What are those? X1. X value is 0. I'm giving the label +1. And then pi by 2. X2 is pi by 2 and I'm giving the label -1. Suppose if I'm considering these 2 points, how will I encode them into quantum states using feature map? Let us see. How will I encode them into quantum states using feature map? Use feature map. Okay, what's feature map? Just see phi of x is equal to, some of you are aware of this notation as well, plus sin x ket 1, cos x ket 1 plus sin x ket 1. Okay. Yeah. So what happens? Let's see. This is ket phi of x. Okay. So ket phi x1. What happens here, guys? If I put x1 is equal to 0, what happens? Cos 0 is 1, sin 0 is 0. So I'll be left with ket 0. If I put pi by 2, phi of x2, if I take pi by 2, both of them will exist. Cos pi by 2. I think if it is pi by 4, it would be good. Pi by 4 would be 1 by root 2 ket 0 plus ket 1. Okay. That would be good. Now, once I finish the feature map part, let's compute the kernel matrix. How do we compute the kernel matrix is what we will see. Okay, I have defined it. In the working rule, I have defined kernel matrix in one version, of course, the inner product version. Phi of x1, phi of x1. Okay, squared. This would be 1. K22 also would be 1, guys, because I know that the computational basis ket 0 and ket 1 are orthonormal. Orthonormal means what? Or they form orthonormal basis. That is, if inner product is 0 for two different states, and for two similar states, inner product is 1. Okay. So again here, phi of x2, phi of x2. This is equal to 1. And of course, let's see this K12. How will K12 be? Phi of x1, phi of x2. This would be nothing but, all of you know how to find inner product, right? Yeah. Of course, ket 0 is what I have to be phi of x1. So I will take bra 0 or dual of 0. Okay. Dual of 0 would be something like this. And then ket 0, ket 1 by root 2 is what I have, whole square. Okay, so yeah, I can just tell you, recall again, ket 0 is 1, 0, guys. So bra 0 would be the dual of it or the transpose of it. It is the row vector. Instead of the column vector, it is row vector. Makes things compatible for multiplication. Okay, so I'll be having 1 by 2. Accordingly, I will write the kernel matrix, guys. Kernel matrix Kij is nothing but K11, K12, K21, and K22. And mind you, once I'm doing all these things, orthonormality and all that, A transpose would be A only. Okay, so what I will have would be 1, 0 0.5, 0. Both would be equal is what I'm saying. Okay, K12 and K21 would be equal. Okay, yeah. Now, once I have the kernel matrix, I pass this to the Classical SVM. Okay, step 3 would be 3. Step 3 would be pass it to classical SVM. I have written the code also. Okay. Once you pass this kernel matrix to SVM, what SVM does is SVM finds a hyperplane, finds a hyperplane separating +1 and -1 using this kernel. Using this kernel with K12 is equal to 0.5, it learns that the 2 points are somewhat similar and not orthogonal. 0.5, it learns that the 2 points or two functions, whatever, 2 points are somewhat similar and not orthogonal. Okay, if suppose if I am inserting a new point x3, let x3 is equal to pi by 3 be the new point. It would be encoded as phi of x3. How do I write it? This is equal to cos pi by 3 get 0 plus sin pi by 3 get 1. Okay, of course you can check the value. You know what's cos pi by 3. You also know what is sin pi by 3. Okay. So hence the classifier would accordingly predict saying -1 or +1 depending on its closeness to the kernel similarity. Okay. Yeah, check this value. What does it do? The classifier would predict +1 or -1 according to its closeness to the high kernel similarity. Okay, this is how we will solve a problem. Of course, you can ask, ma'am, when you are able to do manually this problem, why are we going to give it to the solver, SVM solver? Of course, not all problems are as simple as this. This is just a matrix formed with real numbers, and in quantum, I have no limits. The matrix usually is a Hermitian, unitary kind of things because it has complex numbers as well. That's the reason to solve such things, we give it to the classical SVM solver and hence get the things trained. And once a new data point is being given, the classifier once trained on this gives the predictions. Okay, I think I'm partially clear about quantum SVM. Of course, it is not so tricky, but at the same time not so easy as well. Okay, yeah. There are different options as well. Instead of inner product, I can go with quantum swap. Instead of feature maps, I can choose something else as well. Okay, normalizing the function or vector kind of things. Okay, yeah. Thank you.